Hello guys, welcome to the second and third video of natural language processing on word embeddings and representation. I combined video 2 and 3 because they are of similar topics. Now, word embeddings are basically numerical representations of text. There are different types of word embeddings. Last week, we learned about frequency-based embedding, which is count-based word representation using one-hot encoding. The second one is bag of words, and the third is TF-IDF. Basically, we count the frequency of words in a document or a corpus. Today, we will learn prediction-based embedding to predict words using word-to-vec and deep neural network. Now, word-to-vec, fast text, and glove are examples of prediction-based word representation. The first example of a prediction-based word representation is word-to-vec. Word-to-vec is based on the simple concept that you can derive the meaning of a word based on the company or the neighboring words. So there are two varieties of word-to-vec, the continuous bag of words (CBOW) model and the continuous skipgram model. The CBOW model learns word embeddings by predicting the center word based on its context, which is the diagram on the left, and skipgram learns word embeddings by predicting the context or surrounding words of the center word. Now, word-to-vec trains a shallow neural network. The input layer of the neural network has as many neurons as there are words in the vocabulary being learned. The hidden layer or projection layer is said to have a pre-specified number of nodes, depending on how many dimensions you want in the resulting word vector. If you want to create 100-dimension word vectors, the hidden layer will have 100 nodes. So for example, for CBOW, we want to predict the center word, which is spiky. And we have the context word, which are pineapples, are, and yellow. So these are the vocabulary we use to train this neural network. So when we put in this input, pineapples, are, and yellow, it will go into the projection or hidden layer and predict the word spiky. So now we know pineapples are spiky and yellow. As for skipgram model, it's the other way around, where we want to predict pineapples are and yellow from the word spiky. However, word-to-vec does have its own limitation. Now, word-to-vec cannot cover the morphological similarity. It represents every word as an independent vector, even though many words are morphologically similar, like teach, teacher, and teaching. It can't differentiate them. It acts as an independent vector. It is also hard to conduct embedding for rare words. Now, word-to-vec is based on the distribution hypothesis, works well with the frequent words, but does not embed the rare words. Same concept with underfitting machine learning. So when we have some rare words in a document, it's hard for word-to-vec to conduct embedding for them. But when we write codes, usually we can set the minimum size to, let's say, 1. So that means even it's a rare word, it just appears once, we will still count it in. Now, third limitation is cannot handle the out of vocabulary. Now, word-to-vec does not work at all if the word is not included in the vocabulary or the input. Fast text and glove deals with word-to-vec limitations, where fast text breaks words into several n-grams and glove focuses on global occurrence count. Next, let's learn about deep neural network for NLP. In neural network, there are input layer, hidden layer, and output layer. Weights are sandwiched between the layers. Now let's have a closer look. Here's an example of a multi-layer feed-forward neural network. The input layer consists of the words we use for training. Let's call them X. So we have X1, X2, and X3. X will be multiplied by the weights W and add to the bias. W, the weights are initialized randomly. Now, the number of dimensions in the hidden layer will be determined by us. In this case, we make it 2. Because this is a multi-layer neural network, the output from hidden layer will become x again and multiply by the weights. So the output from the hidden layer is the blue color boxes, and it will be multiplied by the weights again, and the final output will be the predicted word. And back propagation will also be performed to fine-tune the model based on the error rate, which is the red color boxes. Now, I've mentioned about the weights in neural network and how we initialize it randomly and multiply with each of the vectors to eventually create the Y output. Now, in neural networks, the key technique to arrive at the optimum weights is the gradient descent algorithm. This algorithm relies on a hyperparameter called the learning rate. Our main aim here is to minimize the cost function, which is the y-axis here. Alright, so that's all for our video today. Thank you so much for listening, and I'll see you in the next video.